How you doing, sir? Wonderful.
All right, so the goal for today is to finish off your homework number 3 material. Hopefully you haven't been procrastinating on starting that. I know that the Ohm's Law lab was a little bit of a tough lift this week because it's ahead of where we are, but that should be rectified. We'll do a problem session this coming week, which I know we'll have gotten to all the material on, and then the week after we have the holiday that has kind of been messing things up. I've been actually looking to make sure that we're going to hit our marks, but I do believe that the week after that we'll have our first exam. So I'll make that announcement officially shortly. So that'll cover the first 4 homeworks. So we got one more homework after this. Okay. Any admin or logistical questions before I jump in? Okay, so we're looking at making sure we can shore up the relationships between electric field and voltage, making sure we can jump back and forth between the 2 pictures whenever we want to. Here's kind of where I ended last time. I had a uniform electric field. So here's a stronger field. And then here's a weaker field because the black lines are further spread apart. And what I said was that for a stronger field, the equipotentials are also closer together. So think of basically those going together. Electric field lines closer together, equipotentials closer together. Okay? So basically the reasoning for that, so strong electric field, closely spaced equipotentials, weaker field, more sparsely spaced equipotentials, is because with equipotentials we agree to draw them at equal voltage spacings, and I want to reiterate again why they have to be like this. In the top picture, if I drop a charge here, by the time it moves across the diagram, the charge is sped up a lot. So the final velocity is large. If I release one over here, the final velocity by the time it moves across the diagram is not nearly as much. So what's the reasoning? Well, in the field picture, a larger field exerts a larger force on a charge, causes a larger acceleration. So we have more speed change, more speed up, I guess I can call it. If we go through that same reasoning in the energy picture, going across the diagram, we have to have a larger change in voltage overall, so many more equipotential lines if we're drawing them at equal voltage spacing. So a larger voltage change, which means a larger drop in potential energy. And where does the potential energy go? It goes into kinetic energy. So whether we reason it with acceleration or we reason it with kinetic energy, in both cases we conclude that ultimately what we would measure in a lab is that the charge will speed up more. Okay? So hopefully that gives you some idea. In fact, I might even make a graph. Let's say I have my r-axis going this way. I can make a plot of what happens with the voltage versus R. Notice in both cases that I am going to lower voltage. Let's draw a graph. So what does the voltage look like versus R in both cases? I don't really have an origin set yet, so I'm going to just draw it as kind of like a segment here. It's going to look something like this. I haven't yet set an origin or anything, so I'm just going to draw what its rough shape is. I'm not going to try to place it in terms of where it lives. We'll do that later today. And we see the voltage dropping, but it is dropping at a constant rate. Okay? So remember, and this is something that you, hopefully the electric field mapping lab from last week kind of gave you a little bit of a preliminary sense on this, that the electric field can be obtained by the rate of change of the voltage. And on this graph, it's actually the negative of the slope. Okay? So, if the voltage changes linearly, then of course we know that for a linear shape, the slope is constant. Here my slope is negative, which means my electric field is positive. So it points in the positive R direction. There it is. Electric field points towards lower voltage. It's pointing the way down the ramp. The electric field points the way towards lower voltage. And in fact, if we agree to draw our equipotentials at constant intervals, those would be represented by even tick marks on the y-axis here. And I want to point out that since this incline is a flat surface, it's not curved in any way, that does produce equal distance tick marks on the horizontal axis. So that tells us the equipotentials have to be evenly spaced. Okay? So these are always evenly spaced by agreement. We always draw equipotentials at constant spacing. So these are always even spaced. But since this is a constant ramp, it means that the distances that they have happen to be constantly spaced. So this happen to be of a constant spacing. When we do the next one, we'll notice that the equipotentials are not constantly spaced. I should say not the one below it, but the next example I haven't yet done. Now, what's different about this? Well, nothing, of course, except for the fact that since the electric field is weaker, the slope has to be more flat. So here, the slope is a smaller value. Its slope is more flat, which means that the electric field is weaker, which we already knew. So again, if these voltage values are equally spaced over here, they will still produce equal spacing on the horizontal axis, but that spacing is larger. Okay? So still constant spacing, but further apart. So really all these graphs is a way to visualize the relationship in a different way. And I'm guessing with you guys, graphing is something you're fairly comfortable with, so you can take your understanding about graphs and apply it here. So those are uniform fields. I'm just comparing a uniform strong field and a uniform weak field. The voltage changes linearly with distance, and how strong the field is determines basically the slope of your inclined plane. Okay? I haven't yet done the numbers yet. I'll do that later. But now I just want to look at the rough shapes. I'll come back to this example later with numbers. Are there any questions though before I move forward? Okay, so dealing with only uniform fields, that's no fun. So let's take a look at something else. So if we have a point charge, we of course know that the field weakens as you go further away. It's not going to be constant forever. Looks something like this. So as you go away, the field weakens. Well, if the field weakens, then the equipotentials have to get further apart. So over here, where the field is strong, the equipotentials are quite close together, and then they get further apart as you go out here. There are still concentric rings. Over here, you get to lower voltage. Remember, electric field points towards lower voltage. the electric field always most directly points towards lower voltage, so these are right angles. The electric field will always make a 90-degree angle, with the voltage always pointing the way towards lower voltage. But the difference is that since the electric field is weakening, the equipotentials are getting further apart. So closer by, we see something more like this, and further away, we see something more like this. Okay? Does that make sense?
Mm-hmm.
So let's draw a similar graph. It's not going to be a flat incline anymore. We know that the voltage graph looks something like this. Of course, our voltage, I guess I should draw it. If I say it looks something like this, that would help. We know the function is KQ over R. I've drawn it here for a positive charge, so I guess, oh yeah, I already labeled it as a positive charge. So, what we can see is that the slope is negative, and so the electric field is positive. Now, something you should be aware of here is that it is assumed that the R axis is going away from the charge. So if ER is positive, that means you're pointed radially away. So the R axis is basically going away from the charge. And again, it's not, we already knew that. We already knew that the electric field points radially away from a positive charge, but it's nice to see it on the graph, right? It's literally the slope of the voltage graph. And we see that that slope gets more gradual. And the slope getting more gradual is simply telling us that the electric field is weakening. So over here, the slope had to be the same everywhere, right? Because the electric field wasn't changing. Same slope, same slope, same slope, indicating same field, same field, same field. It was uniform, right? Whereas here, what we have is a weaker field. So we do expect that the slope decreases. That's the beauty. If you have a voltage graph, the slope at any point times -1 is the electric field. Okay? So the electric field points the way towards lower voltage. Over here, it points towards lower voltage and it's stronger. Over here, it points towards weaker field, towards lower voltage, and it's a smaller one. Essentially, the electric field loves to point the way towards lower voltage, but if the lower voltage isn't that much lower, it's not as excited to point you there. Okay? The electric field points towards lower voltage, and the closer that lower voltage is, the stronger the electric field points the way. And then when the voltage changes start to be minimal, the electric field starts to be very small. Okay? So, there we have it. In fact, of course, you guys know from math class that how do you when you're taking the slope, what's the mathematical operation that's taking the slope?
Derivative.
Derivative, right? So you could take the derivative, multiply it by -1, and you get the electric field, and what would you get? You would get KQ over R squared. At this point, I'm going in circles, of course, because that's what I started with, and I integrated to get the voltage. So if I take the derivative, I have to be able to recover the field. I just went in a big circle, right? That's how we got to the energy domain in the first place, was I integrated. So if I take the derivative, I can come back. Does that make sense? Sort of.
So you're saying that the area under the electric field graph must be the voltage then?
That's right.
Uh-huh.
Yes, it would be. We don't really ever do that, but yeah, that's totally correct.
Mm-hmm.
So basically, the relationship between electric field and voltage, basically, you take the integration to get here, you can go back, take the derivative. You have to be a little bit careful with how you do that, especially in Cartesian coordinates, which I'll talk about here in a second, but when we're just talking about one axis where there's any action, like R, it is really as simple as integrating. So if you integrate in one dimension, it goes like this. And if you take the derivative, you just come back. And the only thing that really is messing you up there is a minus sign, okay? So don't forget that minus sign. That makes sure that the electric field points towards lower voltage, okay? For those of you that may have seen these, the analogy with a contour map is pretty much exact. A contour map, what is that? Well, let's say you have a map. No one has paper maps anymore, okay? No one navigates that way. Everyone uses their phone, but you still have seen these, okay? Map, paper map, okay? Well, if you do a lot of hiking, then you may have seen something called a contour map. And that contour map is intended to tell you not just the distances and where these hiking trails are and where their turns are, but how rough is the terrain. So for instance, on a contour map, you will have these lines
They get closer and further.
that are equal elevation lines. And those tell you a lot. So equal delta H lines. Say they might draw one of these lines every, I don't know, 100 feet or something, okay? So those are equivalent to like the equal delta V lines, which of course we call equipotentials. So if you have a hiking trail and you see that that hiking trail goes like this, okay, you're in for a rough day, okay? Because you are going to climb through a lot of elevation and you're going to have a very, very steep hike ahead of you, okay? If you want a more casual hike, you should go where the lines are further apart, right? So, again, if the lines are closer together, that indicates a steep drop. Just like over here, that indicates a steeper drop, right? These lines are closer together, that indicates a steep change. These lines are further apart, it's a more gradual change. So the analogy to an inclined plane wasn't just some random thing from physics 1 that doesn't really relate. It's actually exactly the analogy, okay? Okay. The electric field lines point towards lower voltage. There is also an equivalent for hiking. They don't usually put it on maps unless you're a hydrologist or something and you're studying rainflow. Then you might be interested in what is the way most directly downhill. That's the way that water tends to flow unless there's any other considerations, right? So they call that a gradient line in many applications. It's the line that's most directly downhill, and of course that's going to be 90 degrees to the equal elevation lines, okay? So there's a thing called a gradient, and that's most analogous to the electric field. And this is where Tadashi gets mad at me because in math class, gradients point uphill, and in everybody in the real world, gradients point downhill, okay? Okay, so let me show you some other stuff you can do with this. So far, I've only been working in a single direction called R, but we can do the same thing in several directions. That's because when you're in the real world, the chances of your axis pointing exactly along the same way as the electric field is pretty minimal at times. So what if you had a situation like this, where your x and y axes were like this, but your field was like diagonal or something. So you guys have, I think, at least one problem on your homework like this. And you guys also had a chance to try this out in your field mapping lab, where you had a two-dimensional, tried out the two-dimensional gradient. Now, first of all, don't get me wrong, you can always sort of change the axis and measure the shortest distance here. So that would be your delta R. In fact, that's what you did most of your field mapping lab, right? You just found the shortest distance between two equipotentials, and you use this guy, right? So you guys remember using this?
Yes, sir.
I know I would have been ideal if we had just done it, or we're doing it later, but I'm trying to make the best out of what the weird lab schedule, the way it falls out every semester. But that's what you spend most of the time doing. But sometimes it's annoying to find that distance because it's not, it's like diagonal relative to your axes. So you can actually do something like this. You can actually measure, let me put it in a dotted line just because I feel like it. You can actually just measure how much is the voltage changing when you're walking along one axis, the x-axis. Okay? So you're basically exploring how the voltage changes, but you are restricting yourself to walking in one direction. In other words, you're not walking directly downhill, you're kind of walking diagonally. Okay? So then, you use this equation, and basically, the essence of this equation is to say, if you experience any voltage change during your walk along the x-axis, it means that there's an electric field component in that direction. So if you walk to lower voltage along the x-axis, then the electric field must point at least partially that way, because remember, electric field points towards lower voltage. So if there's lower voltage to be had along the x-axis, there's electric field on the x-axis. Now, I'm not terribly worried about how the signs work out. Mainly, I just want you to know that the electric field points towards lower voltage, but let me show you that the signs do work out. The delta x in this case, I'm walking along the positive, I'm walking in the same direction as the x-axis, so is my delta x positive or negative?
Positive.
Positive. And am I walking to a lower or higher voltage?
Lower.
Lower. Remember, this electric field points the way towards lower voltage, so this must be higher, this must be lower. Okay? So I'm walking to lower voltage. What does that mean about delta V?
Negative.
It's negative. So this extra negative is your friend, because that extra negative cancels off the negative that's in the delta V, so your result overall is going to be positive.
You get a positive.
That means that there's electric field with a positive x component, which we better wind up with, because that's the way to lower voltage, right? So there is electric field pointing that way. Then we can imagine from that same point, but we restrict ourselves to only walking along the x direction. Or sorry, what did I just say? Why did I say that?
Y direction.
I don't know, y direction, okay? So I'm not walking all directly towards the lower voltage, I'm walking sort of to lower voltage, but not most directly. So, same thing, yada, 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 you're gonna get a positive y component. So if you are able to walk along the y-axis and experience a different voltage, then the electric field is something along that axis. So this is E sub y. So it's basically telling you that both of those walks were to lower voltage, both along the x-axis and along the y-axis. But if you had lower voltage walking in both directions, then clearly you are not most directly walking towards the lower voltage. If you actually put these together, you of course will get the entire electric field. The most direct way to lower voltage requires travel in both the x and the y directions, okay? So you guys had a chance to try that out, right?
Mm-hmm. The last one.
Okay, the very last part of the field mapping lab. If we were asked, for instance, to draw V versus x and V versus y, then in both cases we would see lower voltage, right? They might look something like that. We're basically walking if we are walking in the x or the y direction, we're walking diagonally across a ramp. We're not walking directly downhill, we're walking sort of sideways to it, right? Does that make sense?
Mm-hmm.
I have a ramp like this. If I walk one way, the x direction, I'm walking sort of downhill. If I walk y direction, I'm walking sort of downhill. So in both cases, I'm going to experience a lower voltage. The slope of this is, of course, Ex, and the negative slope of this is Ey. There may be different slopes, of course. It all depends on whether, how the ramp exactly is oriented relative to your axes, right? If your ramp is mostly pointing in the x direction, then you will have most of the electric field in the x direction, and then only a little bit in the y direction, okay? So these generally may not be equal unless your ramp happens to be 45 degrees relative to your axes, right? If this is tilted, for instance, you can imagine in the case that the electric field actually points that way, then the electric field becomes all x, right, and no y. So this slope is nothing, this is all of it. Or you can split the ramp between the two axes. Does that sort of make sense? Okay, so with that in mind, what I'd like to do is I'd like to bring back the example from last time. That'll be another case where we can see something. We have that dipole, equal and opposite charges like this. And I had my origin here. And let's go ahead and imagine this in a two-dimensional plane. So I'm going to look on the y-axis as well. So let's take a look at what happens here. Well, we've already graphed the voltage versus x. We found it looks something like this. Okay. Well, let's go ahead and take a look. Right here, do we have a slope? Is that slope 0 or not 0?
Not.
It's not 0. The slope is positive or negative?
It's negative.
Negative. Slope is negative. So that means that the electric field is positive. The electric field at that moment is in the positive x direction, which, by the way, I hope that's not news.
Because it decreases by the way.
Looks like that. Electric field points the way towards lower voltage, and that's the way lower voltage is. I want to point out that the voltage itself is 0, but that doesn't matter. So don't conflate the voltage value with the electric field value. Remember that the electric field is the slope of the voltage, not the value, but the slope. Negative slope to be exact, right? So it doesn't actually matter that V equals 0. That's irrelevant, because it's 0 only because it happens to be going through 0, from a positive voltage to a negative voltage. The slope is something, and the slope tells you about the electric field. That's not to be confused with out here. For instance, out here, the slope goes to 0, right? When you get really far away. That is what tells you that the electric field goes to 0. Which, of course, we know, right? You get really far away, the field goes to 0. Now, another interesting exercise might be to not walk along the x-axis, where we walk right through both of these charges and get these big spikes, but take a walk along the y-axis. So let's sketch what that looks like. So one place where I'm going to start is I know the voltage already at the origin, so I already know that this is 0. Right? If the voltage is 0 here, its voltage is 0 here, right? Doesn't matter which way I walked from, the voltage right there is 0. However, what about over here? What's the voltage there?
2V.
What is it? I heard it over there. It's still 0, right? You're still equidistant from equal and opposite charges. One's going to contribute a positive voltage, and one's going to contribute a negative. So V1 plus V2 is still 0. They're the same charge, and you're the same distance, so they're always going to add to 0. So what does the voltage look like versus Y?
Straight line over the 0.
It's flat. The voltage doesn't change. It's always 0. What's the slope of that?
0.
0. So what's the electric field Y component?
0.
0. The slope and the electric field Y component is 0. There is no electric field. Which, by the way, we know that there is no Y component to the electric field. When we originally did this, we always showed that it always pointed this direction. Right? There is no Y component to it. So my best analogy, if we're talking about the contour maps, I have a hill and a valley, right? If I walk along the x-axis, I climb the hill and then I drop into the valley and I come out, right? Well, guess what I'm doing if I walk along the y-axis? I'm squeezing right between the hill and the valley and I never leave sea level, okay? Does that make sense? So here I'm squeezing between the hill and the valley in such a way that I never leave sea level. Does that make sense? Okay, so you can tell a lot about what's going on with the electric field if you just take the slope, specifically the negative slope, of the voltage graph. Okay? Does that make sense? Okay, so with that, let's just do the numbers. So we'll do the numbers to some of the things we've looked at today. The rest I'll leave to the homework. The first one I want to do specifically is the uniform one. We've been talking about uniform fields a lot today. And we actually know what is capable of making a uniform field. We've discussed, of course, the infinite plane.
Infinite long plane.
So that looks like this. Makes that nice uniform field. I guess let's go ahead and set this to be x equals 0. So here's your plus x, here's your minus x. Now why did I choose x equals 0 at the plane? Because I felt like it doesn't matter, for lack of any better choice. Okay? And I know that the electric field over here is going to be positive sigma over 2 epsilon naught. Okay? So that points in the positive x direction, and we've talked about that field. We derived it. It's available on the equation sheet. You don't need to reprove it every time. Over here, of course, all it does is switch and point in the negative x direction. No big deal. Okay? So let's go ahead and pick some random point to start at. I'll talk about why I pick a random point. Usually we start very far away, but that's not going to be an option here. And then what I'm going to do is I'm going to find the voltage function. So this is all x, so I only need to integrate x. I put it in. It's positive. And it's dx. Of course, that's constant, so there's nothing really to integrate. It just pops right on out.
Negative dot x.
Like that. And I'm going to integrate from x initial, which is wherever I start, to some random x. I don't want to commit to a final spot because I want to wind up with a function, right? I want to leave the upper end floating so I have my function. And then over here, what is delta V? This is going to be V at where I end up minus V at where I start, right?
Mm-hmm.
So let me recopy this. And then, of course, you integrate dx to get x and blah, blah, blah. You guys know that stuff, okay? So, what do I have? I have a linear function. No big surprises, right? Just x something or other, okay? If you wanted to make it look a little more clean, you could make it look like this. Oops. So your voltage as a function of x, I'll just move the initial term over the other side. It's essentially going to be something like y equals mx plus b. Now, what does it look like? Let me draw it for you. B versus x.
Thank you.
Well, the electric field points the way towards lower voltage, so we must find lower voltage going further away in the x direction, further away in the minus x direction. It's going to look something like this. So there we have our inclined plane. Of course, the inclined plane drops off in both directions of going away from the plane, right? You have to find lower voltage. Over here, the slope is negative, indicating the electric field is positive, which we know. It's got to point towards lower voltage. It's over here. And vice versa, over here, the electric field better point towards lower voltage, so it's negative. It points in the negative x direction. So Ex is positive over here, Ex is negative over here. Now, where is the zero? Well, you are going to have to just pick a spot. So at some point at x initial, you get to pick that the voltage is something. So this would be V at x initial. Pick your favorite number, and so pick your favorite x value, x initial, and set V initial there to be your favorite number. I don't know, 27 volts, it doesn't matter. Here's the problem. When you have stuff like this, there's a natural place to tuck away V equals 0, okay? We had this as plus C, and we chose it to 0. That effectively tucked away V equals 0 over here. That's nice because that function happens to have an asymptote, so why don't we just pick it so that the asymptote is 0? We cannot ever possibly do that with a linear function. This will always go downhill. When we get really far away, to x is plus infinity, what's the voltage going to go to? Negative infinity. This is, it drops forever. This is a uniform field. It lasts forever. After you've traveled 1,000,000 miles in the x direction, the electric field is still the same there as always. Okay? If you released a charge on this ramp, and you let it go to lower voltage and speed up, how fast would it be going when you got really far away? Infinitely fast. It can always lose voltage. It's always getting pushed by the electric field, which never dies. So it'd be kind of a dumb calculation. Okay? That's different from over here, where a charge will speed up quite a bit at first because it loses voltage gradually, but then the hill starts to flatten out. And in fact, it turns out that it will achieve a finite speed when you get really far away. It actually gets pushed mostly when you're really close to a point charge, and then gets pushed more gradually later. And it will approach a finite speed. Over here, you will speed up forever. Okay? And so for that reason, you just kind of have to arbitrarily pick. You have to arbitrarily pick a location and set a reference voltage there, okay? So be aware of this. There are several problems on the homework where the voltage function does not play nice, okay? It does not have an asymptote, and if it doesn't have an asymptote, you have to have some place to just arbitrarily pick a reference voltage. It's basically, if you want to know in mathematical terms, it's an integration constant, right? So anytime you integrate a function, you have an integration constant, and you can pick it whatever you want. It doesn't have any practical implication to the electric field, right? The electric field is the derivative. So if you take a derivative of a constant, it goes to 0 anyway. So that's what the whole deal is, that when it's convenient, we can pick the constant to be nothing, but there are some things when we integrate, we have to sort of arbitrarily pick what our integration constant is, okay? So you just pick some spot to have the voltage you want, okay? So that's what this looks like, okay? If you wanted to, you could pick that at your x initial, the voltage is 0. That'd be a good choice. So that would mean that this graph crossed there, right? So that would mean that at your x initial, the voltage is 0. By the way, the peak of this kind of pyramid is at x equals 0 because I put the plane there. What would happen if I chose the plane to be at some other x value?
It's going to cross
It
it.
would just move the thing there. So remember, for positive and negative point charges, we get these nice spikes. But now, because we have an infinite plane, it's like a pyramid, and we can just shift it around wherever we decide to put it. That's where the top of the spike is, right? Just like over here, we put charges here and here, and that's where we see the hills and valleys, right? The next thing I want to do is the infinite line charge. This is also on your homework. And this also, the reason I'm doing it is because I want to show you everything that has a little bit of a twist, okay? So this one, we of course know it looks something like this. The field looks uniform, but we know it's not. You just can't see the electric field's lines getting further apart because they're not in the plane of the board. And r equals 0 here is understood to be at the thing, and then r gets higher as you go further away. So, just in the interest of time, and also not giving away the homework,
Oh, please.
let me just quickly sketch this in. I'm going to put in the electric field. Again, we found this before. It's no big deal. You can grab it off the formula sheet. If you need it in a pinch, you don't have to rederive it. I'm going to pick some arbitrary point to start from. You might question, why don't I start further away? Well, I'm going to show you that there's a little bit of an issue. So I integrate from r initial to some random r value. I want to end up with a function over here. I get this. What's the integral of 1 over r going to be?
ln of r.
ln, blah, 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 ln. And ln sucks because ln does not have an asymptote either, right?
Doesn't accept negative.
So this is going to look something like this. The voltage is going to drop as you go further away, but it never asymptotes, so at some point it's going to go negative. This is actually going to be proportional to negative ln of r. I know it looks like this because, of course, I need the slope to be negative because the electric field is positive, or radially away. So what you're going to have to do is just pick your favorite r value, and in this case, I might pick my favorite r value to have voltage be 0. Just because that's a nice thing to do. My favorite number is 0, I guess, okay? So that means that if you're closer, so let's say that's right here, that means that at this moment, at this point, at this distance, I've called V equals 0. When I'm closer to the rod, I have higher voltage, which in this case is going to be positive. And when I get further away, I'll have lower voltage, which in this case is going to be negative. This function can't be stopped from crossing the x-axis or crossing the axis. Okay? This one we can, right? This asymptotes out, so we choose to have the whole thing above and have all the voltage be positive. Here it cannot be stopped, no matter how hard you try. That's natural log. Okay? You can't stop it from crossing the axis at some point, but you at least get to choose when that is. Okay. So, final thoughts.
We need a lot of those.
Let's finish this homework up. I'm gonna get it in the nick of time. So, let's take another old friend, the ring of charge.
Oh, yes.
Is this the hard one?
Yes.
I heard some groans. It's not that hard. So, we found the electric field along the x-axis here. Again, you just grab it from the equation sheet if you need it in a pinch. All right? So, what if we want to do this? Well, luckily, let me put it this way. Luckily, you can find it on the equation sheet and just throw it in. But unluckily, what sucks is that that integration is annoying. It's not easy. So, yes, you can do it that way if you want to do this as long as possible. You want to take as much time as possible to solve this problem.
All right.
But I'll show you a better way.
Hey.
We can actually do direct integration of voltage too. So remember we did direct integration of electric fields? That was what homework 2 was all about.
Yes.
So you had several very challenging problems at the end where you had to do this yourself. Well, we can do that with voltage too. Now, if you're worried this is going to be even harder, it's way easier. The reason why is that if we pick a dq here, it's going to contribute a small amount of dV to this point in question, and the beauty is that is not a vector. It is a number. So we don't have to worry about how the components cancel and the y's cancel and the x is reinforced, none of that crap, okay? So all we're doing is we're taking our point charge formula, which by the way, don't forget that this has built in a 0 already. So in case you're wondering why you're not choosing a 0, you already essentially did it. And you are going to apply the same ideas. We're going to say, chop a little segment of this ring off that has the charge dq, and it's going to contribute a small number dV to the voltage. So, for instance, we pick this as R, this is X, this is the capital R, which is the radius of the ring, and what are we going to do? R will be Pythagorean theorem. Yes?
Yes, sir.
Okay. I want to point out for the ring that both X and R are constant for every dq. So this is going to be the easiest integration in the world. Okay? When I integrate,
It's literally Q.
it's just getting back Q. And that was so much easier.
Oh, yeah.
Okay? I'm done. Oh, I guess I should write it like this. This is dq because I'm still doing this, and then v, I go ahead and copy this. So I just integrated dq to get q. How easy was that?
Do you have boundaries though?
Integral of dq? Sure, yeah. I have integral, I integrate from 0 to q, right?
Yeah.
In fact, I would suggest to you that this is so easy that probably by far the easiest way to find the electric field of this configuration is to get this and then take the derivative. That's not the order we learn things, of course, but it's often much more easy to find the voltage first and then take the derivative. The x component would be this, and we can already by symmetry know that the y component is nothing, so it's that easy. And of course, you should wind up with the same answer that you got from the direct integration of the field. So these are kind of the tips and tricks that you can do. We learned how to get this by direct integration. We just talked about how to get this by direct integration. I didn't talk about it a whole lot because it's basically the same things you've already learned, but even easier, because you don't have to worry about components. So we can get this by direct integration, we can get this by direct integration, and we can then also use the relationship between them to get back and forth. So it gives you lots of options to get all of this stuff. Okay, so that is the end of homework 3, and that is going to be all set then.